What if black holes aren't the most terrifying objects in the universe? What if there's something even more catastrophic lurking in space? Something so alien it could rewrite reality itself? Welcome to Gravastars. These theoretical cosmic destroyers don't just bend space-time, they shatter our understanding of physics and might be responsible for the most violent explosions we've ever witnessed. And the most terrifying part? We might not even know they exist until it's too late. To understand why gravastars are so terrifying, we need to start with a moment of cosmic violence so extreme it defies imagination. Picture this: a massive star, dozens of times more massive than our sun, reaches the end of its life. In its final moments, the star's core temperature soars to billions of degrees. The nuclear furnace that has burned for millions of years suddenly runs out of fuel. What happens next is nothing short of catastrophic. In less than a fraction of a second, we're talking milliseconds, the star's core collapses under its own gravity. The pressure becomes so intense that atomic nuclei are crushed together. Electrons are forced into protons and matter itself begins to break down. This is gravitational collapse at its most violent, and it's here that our cosmic horror story truly begins. Traditionally, we've believed that this collapse leads to one of two outcomes: either a neutron star, where matter is compressed to unimaginable densities, or a black hole, where matter disappears into a singularity of infinite density. But in 2001, two physicists named Paul Maser and Emil Mottola proposed something far more disturbing. What if the collapse doesn't create a black hole at all? What if it creates something even more alien, a gravastar? Unlike the clean mathematical elegance of a black hole, a gravastar is a cosmic abomination that exists in a state of perpetual tension between creation and destruction. Imagine an object where the very center isn't a singularity of infinite density, but a region of space filled with dark energy, the same mysterious force that's accelerating the expansion of our entire universe. This dark energy core exerts a negative pressure so intense that it prevents the final collapse, creating a cosmic standoff between the most fundamental forces in nature. But here's where it gets truly terrifying. Surrounding this dark energy core is an ultra-thin shell of exotic matter. Material so strange that it exists in a quantum state we barely understand. This shell is thinner than an atom, yet somehow contains gravitational forces that would normally crush entire solar systems. It's like a cosmic pressure cooker operating at the very limits of what physics allows, and if that shell ever fails, the consequences could be catastrophic beyond imagination. To truly grasp why gravastars are more terrifying than black holes, we need to dive into the quantum mechanical hellscape that exists at their core. Black holes, for all their cosmic horror, at least follow rules we can understand. They have event horizons, clear boundaries beyond which nothing can escape. They have singularities, points where our physics breaks down, but at least we know where that breakdown occurs. Gravastars throw all of that comfortable predictability out the window. Instead of a singularity, the core of a gravastar contains what physicists call a false vacuum or dark energy state. This isn't empty space. It's space that's actively fighting against the fundamental forces trying to crush it. Imagine a region where the very fabric of space-time is under such extreme tension that it's constantly on the verge of either exploding outward or collapsing inward. The mathematics behind this are genuinely disturbing. In a gravastar, the pressure and energy density follow an equation of state where pressure equals negative energy density. This means the core is exerting an outward pressure that's exactly equal to the inward gravitational pull, creating a cosmic Mexican standoff that could last for billions of years, or collapse catastrophically in an instant. But the real nightmare begins when we consider the quantum effects. The ultra-thin shell surrounding the dark energy core exists in what's called a Bose-Einstein condensate state, a quantum state of matter so exotic that it only occurs at temperatures approaching absolute zero. Yet somehow this quantum condensate is maintaining its coherence in the most extreme gravitational environment in the universe. It's like trying to maintain a delicate house of cards in the middle of a hurricane. The shell itself is where the laws of physics start to break down in truly terrifying ways. Here, quantum mechanics and general relativity don't just disagree, they engage in an all-out war. The shell experiences what physicists call infinite blue shift, where photons trying to escape are stretched and compressed in ways that should be impossible. Time itself becomes distorted, not gradually like near a black hole, but in sudden, violent quantum jumps that could tear apart the very concept of causality. And here's the most disturbing part. Unlike a black hole, which at least has the decency to hide its singularity behind an event horizon, a Gravastars quantum nightmare is potentially visible to the outside universe. If the shell is transparent to certain types of radiation, we could be looking directly into a region where the fundamental laws of physics are locked in mortal combat. Now you might be thinking, how could anything be worse than a black hole? After all, black holes are cosmic vacuum cleaners that devour everything in their path, stretch you into spaghetti, and trap information for eternity. But compared to Gravastars, black holes are actually quite well-behaved cosmic citizens. A black hole follows predictable rules. It has a clearly defined event horizon. Cross that boundary and you're doomed, but at least you know where the boundary is. The gravitational effects decrease predictably with distance. Most importantly, a black hole is stable. Once formed, it will sit there for trillions of years, slowly evaporating through Hawking radiation in a process we can calculate and understand. Gravastars, on the other hand, are cosmic time bombs with no clear expiration date. The delicate balance between the dark energy core and the exotic matter shell could be disrupted by the smallest quantum fluctuation. And when I say smallest, I mean fluctuations at the Planck scale. Variations in space-time so tiny that they exist at the very foundation of reality itself. But the real terror comes from what happens when that balance is disrupted. A black hole, even a supermassive one, affects only its immediate cosmic neighborhood. Its gravitational influence extends far, but it follows the inverse square law: double the distance, quarter the effect. Gravastars don't play by these rules. When a gravastar becomes unstable, it doesn't just collapse or explode. It can undergo what physicists call ergo-region instability. This is a runaway process where the rotation of the gravastar creates regions of space-time that are dragged along at faster-than-light speeds. The result is a cascading failure that can propagate outward at the speed of light, potentially affecting vast regions of space. Even more terrifying is the possibility of what Mazur and Mottola called dimensional explosion. If a gravastar's exotic matter shell fails catastrophically, all the matter that would have formed a black hole doesn't just disappear into a singularity, it gets ejected through what they describe as a central hole into a new dimension of space-time. This isn't science fiction. This is a legitimate solution to Einstein's field equations that suggests our universe could be connected to other universes through gravastar formation. Imagine the implications. Every time a massive star collapses, instead of forming a predictable black hole, it could be creating a tunnel to another universe, ejecting matter and energy in ways that could fundamentally alter the structure of space-time itself. And we would have no way of predicting when or where this might happen. Let's talk about the truly apocalyptic scenarios that gravastars make possible. These aren't just theoretical curiosities, they're potential cosmic catastrophes that could reshape the universe as we know it. First, consider the gamma-ray burst connection. Gamma-ray bursts are the most violent explosions we've observed in the universe, releasing more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. We've traditionally attributed these to black hole formation or neutron-star collisions, but gravastars offer a far more terrifying explanation. When a gravastar forms, the violent reorganization of matter and energy could produce gamma-ray bursts that dwarf anything we've seen from black holes. But unlike black hole-produced bursts, which are at least somewhat predictable, gravastar-induced gamma-ray bursts could occur with no warning and with energy outputs that could sterilize entire galactic regions. We're talking about explosions so powerful they could strip the atmospheres from planets hundreds of light years away, but that's just the beginning. Remember that dark energy core? Dark energy is the force driving the accelerated expansion of our universe, and we still don't understand it. A gravastar essentially concentrates this mysterious force into a region smaller than a city. If multiple gravastars exist, they could be creating a network of dark energy concentrations that collectively influence the expansion rate of the universe itself. Here's where it gets truly cosmic in scale. If gravastars are more common than we think, they could be the reason our universe's expansion is accelerating, but this also means they could potentially cause that acceleration to change unpredictably. Imagine if the dark energy cores of multiple gravastars somehow synchronized their behavior. The resulting change in cosmic expansion could tear apart the large-scale structure of the universe, separating galaxies so rapidly that the night sky would go dark within a few billion years. Even more disturbing is the possibility of gravastar collisions. When two black holes merge, we get gravitational waves and a larger black hole. When two gravastars collide, the interaction between their dark energy cores and exotic matter shells could produce effects we can't even begin to calculate. The collision could create cascading failures in space-time itself, potentially opening permanent rifts between dimensions or creating regions where the fundamental constants of physics are different. And then there's the nested gravastar scenario, what physicists call nestars. Imagine a gravastar forming inside another gravastar like cosmic Russian dolls of exotic matter and dark energy. Each layer would be held in place by increasingly delicate quantum mechanical balances, creating a structure so unstable that the failure of any single layer could cause the entire system to undergo catastrophic collapse or explosion. Here's perhaps the most terrifying aspect of gravastars. We might not be able to tell them apart from black holes until it's too late. From the outside, a gravastar looks almost identical to a black hole. It has the same gravitational field, produces the same effects on nearby matter, and even generates the same types of high-energy radiation as material falls toward it. This cosmic masquerade means that every object we've identified as a black hole could potentially be a gravastar in disguise. Sagittarius A, the supermassive black hole at the center of our galaxy, it could be a gravastar. The black holes detected by LIGO's gravitational wave observations, potentially gravastars. Every X-ray source we've attributed to black hole accretion, all of them could be these exotic cosmic time bombs. The observational challenges are genuinely disturbing. Astronomers have been searching for ways to distinguish gravastars from black holes for over 2 decades, and we've made frustratingly little progress. The most promising approach involves looking for gravitational wave echoes, subtle differences in the gravitational waves produced when these objects merge. But even this technique is controversial, with different research groups reaching contradictory conclusions about the same data. Some studies of LIGO's gravitational wave detections have suggested that the signals are inconsistent with gravastar models, but other analyses conclude that the data is indistinguishable from what we'd expect from gravastar collisions. This isn't just an academic debate. If gravastars are real and common, it means our understanding of cosmic evolution, galaxy formation, and even the ultimate fate of the universe could be fundamentally wrong. The transparency question adds another layer of cosmic horror. If gravastar shells are transparent to certain types of radiation, we might be able to peer directly into their dark energy cores using advanced telescopes. But what we see there could challenge our understanding of physics so fundamentally that it would require rewriting textbooks across multiple scientific disciplines. Even more unsettling is the possibility that gravastars could be detectable through their effects on space-time itself. Unlike black holes, which create smooth distortions in space-time, gravastars might produce subtle quantum ripples, microscopic variations in the fabric of space and time that propagate outward at the speed of light. These ripples could be so faint that we'd need gravitational wave detectors thousands of times more sensitive than LIGO to detect them. But if they exist, they would provide a cosmic early warning system for gravastar instabilities. The scientific community's response to the gravastar hypothesis reveals just how seriously physicists take this potential threat. Research into gravastar stability has uncovered some genuinely disturbing possibilities that keep theoretical physicists awake at night. In 2007, detailed stability analyses revealed that rotating gravastars could be fundamentally unstable. Unlike black holes, which become more stable as they spin faster, gravastars experience what's called ergo-region instability when they rotate. This means that any gravastar formed from a rotating stellar core, which would be virtually all of them, could be inherently unstable, existing in a state of perpetual near collapse. Recent theoretical work has explored even more exotic possibilities, including continuous pressure gravastars that don't have the traditional 3-layer structure. These objects would be even more unstable, existing in quantum states so delicate that they could be disrupted by gravitational waves from distant cosmic events. Imagine a cosmic domino effect where the merger of two black holes billions of light years away could trigger the catastrophic failure of gravastars throughout the local galactic group. The nested gravastar research has revealed scenarios that border on cosmic nightmare fuel. Theoretical models suggest that these nesters could form naturally during the collapse of extremely massive stars, creating structures with multiple layers of exotic matter and dark energy. Each layer would be held in place by increasingly complex quantum mechanical interactions, and the failure of any single layer could trigger a cascade failure that releases energy equivalent to multiple supernovae occurring simultaneously. But perhaps the most disturbing recent development is the connection between gravastars and the multiverse hypothesis. Some theoretical models suggest that gravastar formation could create permanent connections between our universe and parallel universes, with matter and energy flowing between dimensions in ways that could fundamentally alter the physical constants in localized regions of space. This isn't just academic speculation. If true, it means that gravastar formation could create cosmic infection zones, where the laws of physics are different from the rest of the universe. Stars in these regions might burn differently, planets might not form properly, and life as we know it might be impossible. The energy exchange between universes could also explain some of the most mysterious phenomena we observe, including dark energy acceleration and the apparent fine-tuning of physical constants. But it also suggests that our universe could be vulnerable to catastrophic changes triggered by gravastar activity in parallel dimensions, threats that we couldn't predict, detect, or defend against. As we reach the end of our journey into the realm of gravastars, we're left with a cosmic question that should keep us all awake at night. If these objects are real, what does that mean for the future of our universe? The implications are staggering. If gravastars are common, then our understanding of cosmic evolution is fundamentally flawed. The supermassive objects at the centers of galaxies might not be the stable, predictable black holes we thought they were, but rather cosmic time bombs that could explode without warning, potentially destroying entire galactic cores and everything within them. The dark energy connection is perhaps even more terrifying. If gravastars are concentrating dark energy into localized regions, they could be creating a network of cosmic influence that extends far beyond their immediate gravitational effects. Changes in gravastar populations could alter the expansion rate of the universe itself, potentially leading to scenarios where cosmic expansion accelerates so rapidly that it tears apart the fundamental structure of space-time. But there's also a paradoxical hope hidden within this cosmic horror story. If gravastars are real, they might provide us with a window into the deepest mysteries of physics. The exotic matter in their shells could teach us about quantum mechanics at cosmic scales. The dark energy in their cores could finally help us understand the force that's driving our universe apart. And the dimensional connections they might create could open up possibilities for physics and technology that we can barely imagine. The race is now on to definitively prove or disprove the existence of gravastars. Next-generation gravitational wave detectors, advanced space telescopes, and quantum sensors operating at the limits of physical possibility are all being developed with the goal of finally answering this cosmic question. But here's the truly unsettling part. We might not like the answer we find. If gravastars are real, we'll need to completely reimagine our place in a universe that's far more dangerous and unpredictable than we ever imagined. If they're not real, we'll have to explain why the mathematics of general relativity and quantum mechanics seem to predict their existence so convincingly. Either way, the gravastar hypothesis has already changed how we think about the most extreme objects in the universe. These cosmic destroyers, whether real or theoretical, have shown us that the universe still holds secrets that could fundamentally challenge everything we think we know about reality itself. The next time you look up at the night sky, remember that among those distant points of light there might be objects so alien and dangerous that they make black holes look like cosmic teddy bears. And the most terrifying part, we might not know they're there until the moment they decide to tear apart the very fabric of space-time itself. Gravastars represent the ultimate cosmic horror story. Objects that exist at the intersection of our greatest scientific theories and our deepest fears about the unknown. They challenge our understanding of physics, threaten the stability of the universe, and remind us that even in an age of advanced science, the cosmos still holds mysteries that could change everything. Whether gravastars are real or remain forever theoretical, they've already accomplished something remarkable. They've shown us that the universe is far stranger, more dangerous, and more wonderful than we ever dared to imagine. And in a cosmos full of black holes, neutron stars, and dark energy, that's saying something. Thanks for joining me on this journey to the edge of cosmic horror. If you enjoyed diving into the terrifying world of Gravastars, make sure to subscribe for more explorations of the universe's most mind-bending mysteries. And remember, the next time someone tells you that black holes are the scariest things in the universe, you can tell them about something far more terrifying lurking in the depths of space.